She out in the car or what?
No, she's in my house. It's just like a quick 20-minute drive.
Hanging.
Oh yeah.
So Caitlin, you brought up a very interesting question about an ellipse. Let me check in with you people. If you have an ellipse, does anybody know what the area of an ellipse is?
Something that Google knows.
That is not what the question was. So this is usually called 0b. This is called a comma 0. Any idea what the area of the ellipse is?
Is this on a 8.4 homework problem?
There is an ellipse in there.
It's a really simple equation.
Okay, so let me ask you this. Say that again.
Pi radius squared.
So if you have a circle, what is the area of a circle?
Pi r squared.
Right, so this distance is r, this distance is r, the area is pi rr, correct?
Yes.
Pi rr, aka pi r squared. So what do you think the area of this is? Pi ab. Yeah.
Oh.
Which is what you're going to see with that problem. Yep.
Is
We're
that-
doing that, right?
Is that on 8.4?
Oh, so radius gets turned into two different things.
Right.
That makes
Yeah.
sense. So it's still the same thing though.
Yeah. Still pi times the short radius times the long radius. Yeah. So it's interesting. Interesting that it never comes up in like a high school geometry class. That seems kind of like a easy fact.
All right. Physics goes up in geometry.
Yeah. Right. Isn't that weird?
We don't like eclipses.
We learned it in algebra.
Okay. So let's go ahead and do some trigonometric substitution. We have one more slide only. Cool. Of trigonometric sub. And then we'll get into partial fraction decomposition. What a terrible word. It sounds gross. Decomposition. Sounds like a septic tank, yeah.
I arrived in my house and it was literally the worst smell. And it's
Wait, okay, what?
my grandpa left the
All right, so when we look at this denominator, it's got three terms. So it's a trinomial. We've seen all these binomial denominators that we could use trig sub for. If we had an x squared plus 4, an x squared minus 9, or whatever, we had binomials. We could use trigonometric substitution. But this is not a difference or sum of squares in the denominator. So we have to use completing the square, and we're going to try to get to a place where we do have something that looks like a trig sub integral. And so the trick here is to complete the square.
Yeah, we're gonna think back.
And when you complete the square, what is the constant that we need for those two x terms to be a perfect square trinomial? What do we need for the constant? So we take the coefficient of x, divide it by 2, and square it. So we would need 9. So we take that, divide by 2, and square it. So negative 6 divided by 2 is negative 3, square it, you get 9. So if we had a 9, that would be a perfect square trinomial. So what we're going to do is take 9 from the 34. If we take 9 from the 34, it's going to look like that. Ooh, that was right in my eyes. So now this part here is a perfect square trinomial. So that part can factor perfect square trinomial, x minus 3 quantity squared. So we will have the integral, and we will have x minus 3 quantity squared plus 25. Now that denominator is a sum of squares. Question?
If we're taking this back to algebra, is that finding like the k value? B over 2 squared?
I don't know what k is. K is the y.
Find hk.
That's the vertex of a parabola.
Oh, okay.
Vertex of a parabola. This is just completing the square. It doesn't have anything to do with the graph.
Okay.
It's just that in order to have a perfect square trinomial, the constant here has to be half of this squared. So half the coefficient of x squared is what you need to make it a perfect square trinomial. Any perfect square trinomial has that pattern. That the constant is b over 2 squared. Now it's looking a heck of a lot like an inverse trig type of integral. It's looking a lot like, hey, we could do trigonometric substitution here. Now, do we need trigonometric substitution here, or do we already know the antiderivative of this? Remember that arctan, oh, that's dead. We don't actually need trig sub here. It's already in the arctan form, almost, a little bit of manipulation. Let's factor out the 25. So that 25 is in the denominator. So we're going to factor it out from the denominator. So it's going to give us a +1, because our trig sub form, we like to have a +1. And so there is no 25 in this first term, so we're going to put a 25 there, and it will look like that. So now it's in arctan form, because we know the integral of dx over 1 plus x squared, that is arctan of x. So now it's in that form, except that we have to add a little wrinkle called RCR. We have to reverse chain rule it, because that's not just an x, that's a function of x. What's the derivative of this function of x right here? What's the derivative of that right in there? 1/5. 1/5 is the derivative. So when we do RCR, we'll have to divide by 1/5, which will turn into multiplication by 5. So this, we can actually cut right to the chase here. Well, 125, I'm going to leave space for RCR. Leave a little space. Then we're going to have inverse tangent of x minus 3 over 5. And then the derivative is a fifth. Dividing by a fifth is the same as multiplying by 5, so that goes in right there. So this is because of RCR right there. First chain rule. So if we simplify this, we'll get 1/5 arctan x minus 3 over 5 plus c. There is our answer. All right, questions on using completing the square on that problem? Yeah, Ari?
Why does that one say?
Why is it so easy?
Yeah.
Because the power in the denominator, if we look at the whole denominator, the power is 1. We don't have a big square root or a 3/2. Like all of these other ones were more complicated because there was some other exponent in the denominator going on. So the denominator here, the focus on this first one is to do the completing the square part. So we don't really need trig sub here. So that's why it's easier. Let's try this one. So once again, it's a trinomial. Trinomial isn't in the right form, so we have to do it completing the square. But as you learned in college algebra, or whatever you took in algebra, you cannot complete the square when there's a leading coefficient other than 1. So the first step is to factor out that leading coefficient so that we have a trinomial with a leading 1. So we're going to have u squared minus 6u plus 18. Oh, is it a 6 again? Good grief. Oh, I got to change that. So once again, we have to complete the square. So we take the coefficient of x, divide it by 2, and square it.
Question.
Okay, so once again, we're going to need a divide by 2, get a 3, square, get a 9, so we need a 9. All right, so we're going 1/2 integral du over, so we're going to take 9 away from the 18 so that we have a perfect square trinomial. So that right there is now perfect square. That will factor very nicely. We're going to have du in the numerator. Let's see, so u minus 3, quantity squared, plus 9. All right, you all finish it off. Write down the last step, or the last 2 steps. There's 2 more steps. Let's see if you can finish it off based on what we did on the top one, because it's very similar. You can write down the answer. Let me know if you're snagged. Give you a kick. So this is very similar to the last one. We want to factor out the constant. We know it's going to be an arctan. So we factor out that 9. Yeah. So if we factor out the 9, we get 1/18 out in front. There is no 9 in this first term, so factoring out the 9 introduces a 9 in the bottom. But then we want to write it as a single square, so it's going to be u minus 3 over 3, quantity squared. If you wanted to do substitution, you could, and you would let u be this, but we already know how to deal with substitutions that are linear. That's a linear substitution, so we can just jump to RCR. So we are going to have 1/18. We'll leave a little gap for RCR. That's arctan. So arctan of u minus 3 over 3. What's the derivative? Derivative of that yellow piece is 1/3. So we're going to multiply by 3, add c, and that is our answer. So 1/6 arctan u minus 3 over 3 plus c. So completing the square, it's a technique.
This kind of might be a dumb question. If we have to do a u substitution on a problem and we're given it in terms of u already.
I will never give it to you as a
Okay.
u on the test.
Okay.
It's all going to be x's.
Okay.
No y's, no z's,
No T's?
no t. Well, there might be some t's, but no u's.
Got it.
V's. I don't know why they love to do that to us.
So I'm like, wait, do I still have to back substitute?
Yeah, exactly. That's what it feels like. All right, so let's go to PFD then. So PFD, partial fraction, unless someone has another question from anywhere, any trig sub question you have? Trigonometric sub. So PFD, it is a technique that once you get used to is actually one of the easier techniques. Trig sub is one of the harder ones. This is one of the easier ones. And if you look, PFD is something that you've done in the opposite direction. So if we look over here, If you had two fractions and you wanted to combine them into one, you would get a common denominator and add them. And so that's what you've done, since you started algebra. PFD is the opposite. It is, let's take a rational function and let's break it into these smaller fractions. So we want to bust it down into fractions where the denominator is filled with linear expressions. So the decomposition is that. It's taking this quadratic and decomposing it into linear expressions. So that's what the decomp means. And I think it's pretty obvious that if you were integrating both of these forms, the integral of this form on the right is way easier, right? Those are logs. We can evaluate those super easily right here. Right? This is just going to be the natural log of the absolute value of x minus 2 plus 2 times the natural log of the absolute value of x plus 4 plus c. So if we can get to this spot here where we can get a partial fraction decomposition, it's usually way easier to integrate. That's usually the way to integrate it. So over here, we could try to complete the square. This might have another technique that will work, but PFD, if you can break it apart into little fractions and partial fractions, it's going to be pretty darn quick.
Where does the x go?
It vanishes because when you get your common denominator here, it will be created, right? So if we started with this, we would multiply the first one by x plus 4 over x plus 4. We would multiply the second one by x minus 2 over x minus 2. And so our common denominator is going to be that product. And when we do the math here, we end up with 3x plus 4 minus 4, so 0, divided by that denominator. So that x in the numerator is coming from the common denominator process of adding the fractions together. That makes sense? So it's really important to sort of look here and realize that these are linear factors. And so this will be the simplest case where we turn a quadratic into linear factors, or possibly turn a cubic into linear factors. We cannot always get to linear factors in the denominator, but we can always get to quadratic or linear factors. And if we have quadratic factors, we've already done integration with quadratic factors, right? We've done completing the square, we've done inverse trig functions, we've done trig sub.
And then how do you know when to make partial fractions rather than complete the square?
You'll be told. So on the test, it will just say, use PFD or use completing the square. So yeah, you'll be told. If you can do PFD, usually that's going to be easier. Okay, so here's what generalized PFD looks like for linear factors. So it looks looks way more complicated than it is. Just notice in the denominator, that's really happening again, huh? So in the denominator, we have all these I don't know why they put parentheses around them. It's just a bunch of linear factors. So whatever the denominator factors into, and there's a theorem that you have heard of before called the fundamental theorem of algebra. The fundamental theorem of algebra says that if you have a polynomial, it can always be factored into powers of linear and irreducible quadratic factors. An irreducible quadratic is like x squared plus 1. You would need imaginary numbers. So x squared plus 1 is irreducible. So fundamental theorem of algebra says that this is possible, that we can factor into linears and irreducible quadratics. We're just looking at the case where the denominator q factors just into linears, distinct linears. So that's where we're starting. Looks more complicated than it is. All they're saying is once you have the denominator totally factored into linears, all you have to do is this. You take your integrand. So we're going to take this given integrand, and we are going to create a structure that looks like this. We're going to create a fraction with the x minus 2 factor and a fraction with the x plus 6 factor. And there will be constants, numeric constants, for which that equation will be true. And that is our goal. Find A and B. Now we're back to algebra 2, if they call it that anymore. Intermediate algebra, if they call it that anymore. Math 2.
Math.
Math with x. So this is just an algebraic equation that we have to solve for A and B. So we're going to multiply both sides by the denominator on the left, clear out the fractions. So we're multiplying both sides by x minus 2 times x plus 6. So we're taking this entire equation and we're going to multiply by x minus 2 and x plus 6. So when we multiply the left side, it wipes out the denominator. When we multiply on the right side, that whole expression there is going to be distributed. It's going to be distributed to the a fraction and the b fraction. When it distributes over to the a fraction, the x minus 2 in the denominator will cancel with the x minus 2 in the numerator, giving us a times x plus 6. When that expression gets distributed to the b fraction, the x minus 6 in the denominator will cancel with the x plus 6 in the numerator, leaving us with the b and the x minus 2. So we'll have plus b times x minus 2. Good? Now, we are going to solve this for A and B. So solving that for A and B, there are two techniques that we will use. Let's use the traditional technique first, and then I'll show you another technique that works really well when you have only linear factors. So for the traditional technique, all we do is multiply everything out. So we're just going to do what I think would be instinctual if you were left to your own devices. On the right-hand side, I'm going to group things. That should be a 6a in there. So we're going to group things on the right-hand side strategically. I'm going to look at the term that has an x in it, and I'll factor out the x. I'm going to write it like that. Now the left side, I'm going to write like this. 0x plus 8. The left side is a polynomial. The right side is a polynomial. The only way two polynomials can be equal is if corresponding coefficients are the same. It's the only way. It's the only way two polynomials can be equal. If we have something like ax cubed plus bx squared plus cx plus d equals 4x cubed minus 2x squared plus x minus 3, What does A have to be? 0. So if this polynomial is equal to that polynomial, if you plugged in a 0 there, then this polynomial would have no cube term, so then they would no longer be equal. What does the A have to be for those two things to be equal? 4. You see it? So the A has to be 4. If somebody says this polynomial equals that polynomial, well, then the coefficients of the x cubes have to match. They both have to be the same. So if this one's a 4, then that has to be a 4. What does the B have to be? -2? -2? What about the C? What does the C have to be? 1. What does the D have to be? -3. Right. So if we come over here and we look, these are both polynomials. The polynomial on the left has a coefficient of x that's 0. So the coefficient of x on this side has to match the coefficient of x on the other side.
So A plus B is 0.
So A plus B is 0. And similarly, the constant on the left, which is 8, has to match the constant on the right. The constant on the right is the stuff with no x's, so that's 6a minus 2b. So the traditional method uses the concept that two polynomials are equal if and only if their coefficients match. And then we go to either the elimination or the substitution method down here, and we solve for a and b. Now let's first simplify this second equation. We can divide out the 2. So let's divide out a 2. And if we divide out a 2, we get that. And here you can use elimination or substitution, whatever is your favorite linear system technique. Looking at this, in my mind, the simplest way is just to add these equations. So this is called the elimination method. If we add those equations, which letter is going to disappear? If we add those, the b's are disappearing. So this is called the elimination method because we're eliminating one of the unknowns. So if we add the left, we get 4. If we add the right, we get 4a plus 0. So this tells us that a must be equal to 1. So there's a. And once you have a, how do you think you get b? Yeah, plug it back in. Backs up. So we can plug it into any of the equations up here. So once we know that a is 1, if I plug a in 1 right there, what does that tell us b has to be equal? -1. -1. You can plug it into either equation. If you plug in a right there, you would get 3, subtract 3 from there, you get 1 equals -b, so b is -1. Right? Yeah. Teach that to a chicken.
Good luck.
Right? Okay, so that is the traditional technique. Let's see where that takes us then. So let's just come over to the side. So our integral, let's call it something. We've been using omegas. Let's stick with that. I'm just going to call that omega. So that integral omega is going to be equal to now the integral of, we found a to be 1, so it's going to be 1 over x minus 2. We found b to be -1, so it's going to be -1 divided by x plus 6 dx. So now we have done PFD. We have done partial fraction decomposition. This over here is a quadratic. If we multiplied it out, it's x squared plus 4x minus 12. So that quadratic, we've reduced it into these two partial fractions. And integrating this is pretty straightforward because we have both these are in log form. So we're just going to take the natural log of the absolute value of the denominators, and we are good to go. Woo. So now, okay, plus c. And we could, of course, combine these if we want. I'm not going to ask you on the test to combine, but since we have all the time in the world here, that would be our answer. Okay, how'd that feel? Better than trig sub, right? And especially after we do a few, you'll definitely get the hang of it. Okay. So any questions on any pieces there, Ari?
Can you show us the non-traditional?
Yeah, we'll do that on the next slide. Yeah, we'll do it because we're going to use the non-traditional. The traditional method is, of course, longer than the shortcut method.
I'm not sure you could teach this to a chicken.
Yeah, maybe not.
So is this the method that we learn in algebra?
Yeah.
You're going to teach us something new?
This is the technique you should have learned in algebra, yeah.
Yeah, the traditional is what we should have learned in algebra.
Yes.
And what you're about to teach us is new.
Something new.
Okay.
Yeah, we'll call it the convenient value method.
Okay.
I mean, so the new method only works for linear.
It works best for linear.
Okay, so
Works best.
would you say it's better to default to the traditional?
It's better to default to the traditional originally because you have to use the traditional method when you have irreducible quadratics.
Okay.
So when we get to the more complicated denominators, this is the best method for sure. So do enough of this method so that you're comfortable with it, and then you can do the shortcut method once you get this
But the
down.
shortcut method is more of like an optional
Yeah.
thing. Like
Yes.
you can do everything with the traditional.
Yes.
And you'll use the traditional way more, but the shortcut method just gives you a shortcut sometimes.
Sometimes.
Like Harrison said.
Yeah, yeah, exactly. Exactly. The Harrison technique.
Huh?
Yeah, we knew you were listening. Okay, so
Shortcuts.
let's try this one.
Like 20% of the time, but it works 100% faster.
It's amazing how 20% seems big to some people.
All right.
So
I passed.
the first thing we want to do is, so you saw that the denominator in the last one was already factored. So when we start PFD, we want to have that denominator factored. So that's going to be our first step here. So first we'll factor out the x. And we want to factor all the way down till we can't factor anymore. That is a quadratic that is reducible. Differences of squares are always reducible. If it was a sum of squares, it would not be reducible.
Should we factor the numerator as well?
Nope, just the denominator. So the denominator is going to factor into,
Is that in every situation when you don't factor the numerator?
yes,
Okay.
for PFD, yes. Because what we're going to do next is create the framework for our PFD. We're going to have 3 fractions. All right, so now we're going to take our 3 fractions. We're going to take the inside, the whole inside, 4x minus 2. So we're taking the inside away from the integral, just taking the rational expression, rational function. And this has to be a divided by x for some a plus b divided by x minus 1 for some b. So it must be, there must be an a, b, and c that satisfy that. So we're trying to find, we're trying to boil it down to its kind of like atoms. It's essential building blocks. Wow, it's worse than ever. So the first step, once we have written down our PFD equation, the next step is to solve for a, b, and c. And to do that, we first clear the fractions. We clear the fractions by multiplying by the common denominator here. So both sides get multiplied by that denominator.
Could you do this one with both the traditional method and the...
We're going to do it in the next slide.
Oh, we're going to do the fancy one on the next slide?
Yeah.
Okay.
Yeah,
Which one's fancy?
you'll see it on the next slide. So excited. It's the most excited I've seen this class ready to learn. Let's do more. You guys are amped. It's cool.
I was just trying to see them side by side.
Yeah, we'll do them side by side so you can see the difference. Okay, so multiplying the left side by the left denominator, clearly left denominator vanishes. when we take that denominator and we multiply it to the right-hand side, the x here is going to cancel with the x there, and we're going to be left with a multiplied by x minus 1 times x plus 1. When we multiply that yellow block to the second fraction, x minus 1 in the denominator will cancel with that x minus 1. So we're going to be left with bx times x plus 1. When we multiply that yellow block to this, x minus 1 in the denominator will cancel with that x plus 1 in the numerator. So we're going to have that. All right. Any mental drama in going from the first step to the second step? Drama free? So drama free, on the left we have a polynomial, on the right we have a polynomial. So let's distribute this out. We're going to have an a times, let's see if we can do it in one fell swoop. We're foiling here. So first is a squared, and then we have to multiply. The first is x squared, then we have to multiply by a. There's first. Oh, do you see the middle term, no middle term? Because the inner and the outer cancel, so no middle term. And then the last is minus 1 multiplied by a. Here we have bx squared plus bx plus cx squared minus cx. So now we've got our polynomial on the left, our polynomial on the right, and we can set up the system. So the system says the coefficients have to match. On the right, we see that the largest coefficient is an x squared. So I'm going to highlight the x squared coefficients. You could do one intermediate step here and write it and factor out the x squared, but you get it. What is the coefficient of x squared on the left? 0. So if you want to, you can put a 0x squared in there. If you need to do that, that's fine. So that's a plus b plus c. So the coefficient of x squared on the left has to match the coefficients of x squared on the right. Coefficient of x on the left is 4. Coefficient of x on the right is b minus c. Constant on the, let me highlight that too. So this one was yellow, and then let's go with, oh no, that was not yellow. This one was yellow. Coefficient of x is 4, coefficient of x is b minus c. Then our last one, we've got the constant of negative 2, and over here, let's see, that's a constant. That's the only constant. Okay, that's going to make it easy. So constant on the left is -2. Constant on the right, the only term with no x, minus a. So now we just have to solve that system. In this case, we should be able to bootstrap our way up. This says that a is 2. So if a is 2, let's plug that into the top equation so that we have two equations with b and c. So I'm plugging the 2 into the top equation, and I'm going to move it to the left. So I have -2 equals b plus c. Second equation, staying the same. So we've solved for a. Now we have a system that's reduced to just b and c. Once again, it looks pretty straightforward if we just add those. So if we add those together, let's see, we get, on the left we add and get a 2, on the right we add and get a 2b plus no c. So this tells us that b is 1. So we've got a, we've got b, and what does c have to be?
-4.
Close. -3? So if b is 1, right, in the top equation, Subtract 1 from -2, and we get -3 as the C value. Yeah, it doesn't matter what equation you plug it in. If you plug it in down here, subtract 1, you get 3 equals -C, so C is -3. So there's the algebra part. Any piece of that you forgot from college algebra? So the concept again is that two polynomials are equal if and only if their coefficients are the same. No other way polynomials can be equal. They have to have matching coefficients. All right, so the original integral, way back up here. Let's go up and grab it. Again, let's call it something so we can just name it. So that's going to be omega equals. A is 2. So we're going to have 2 divided by x. B is 1, so 1 divided by x minus 1. And then C is 3, -3, so that's going to be -3 over x plus 1. And once again, we end up with a really simple integral, which are just all logs. So we end up with 2 times the natural log of absolute x plus natural log of absolute x minus 1 minus 3 times the natural log of x plus 1 plus integration constant. Right? Not too bad. Not too bad. And again, we normally aren't going to use log properties. It gets to be just tedious. Bring up the 2, bring up the 3, create. You can do it, of course, but you won't be required to on the test. So, yeah, I thought I had it on the next slide. Well, let's do it on this slide. Let's do the other method right now with this one. Gosh, I must have lost the slide somewhere because I could have sworn I had it set up to do it with this one. Daniel, do you have any extra pages in there that I'm missing?
I mean, this whole page is like blank, basically, just with one problem. So it's just this problem.
4x minus 2,
And
x
then-
cubed minus...
The next thing you have is this page.
Okay, huh. I must have deleted it somehow. Okay, question?
Just, am I crazy, or would there not be as many of those logs if you did complete the square?
Well, we can't complete the square here with a trinomial, with a cubic. So we're not going to be able to use, this is not going to have another technique that's going to be very easy. So with the simpler ones, we probably can come up with a completing the square technique that's going to work fine here. But this one, definitely not going to be able to do that with. Yeah.
What's the highest exponent and denominator that we're expected to work with? Because like I'm assuming this would work if you had x to the 99th, but no one wants to do that.
No one wants to do that, and no one would ask you to do that. We're going to probably see as high as a 4. Maybe.
As a 4, okay.
Yeah.
You have to start inventing new letters.
Yes. It's possible. Start using little symbols. Okay, so let's try this same one,
64.
but with the other technique. So let's grab that. Where's my lasso? So let's grab that. Didn't I create a copy up there? Did I not create a copy up there? I guess we can just hold it and we'll ask me to copy it. All right, so let's go down here. Let's try to go down.
You're on cell last year.
There we go. And let's do this with the other technique. So the first thing we did was factor. So let's get to this point first. So we had x, we have x minus 1, we have x plus 1. Okay, so those are all linear. And the thing that we are trying to solve, I'm going to grab the equation from up here So we had 4x minus 2 equals, and this is where we're at. So let's go to that. So a times x minus 1 times x plus 1. So b times x times, is that x plus 1? And then c times x. Okay, so this equation is our PFD equation. This is the equation where we decide whether we're going to use traditional or this method I'm about to show you. Question?
What's the name of this method?
The convenient value method. So that's what we're going to do now. We'll do it with the convenient value method. Convenient value method. So notice this equation has no division. Right? There's no division. This equation is defined for every value of x. Any real number x you put in there, it's defined for. No mystery there. In particular, it is defined when x is equal to 0, when x is equal to 1, and when x is equal to negative 1. So those convenient values are the zeros of the three, bless you, of the three factors. So those are the convenient values. The convenient values are the zeros for those three factors. This equation is defined for those zeros because we no longer have a denominator. So that equation, the PFD equation, is true for all x. Notice what happens. So we plug in 0 across the board. So plug in 0 on the left, we get negative 2. Plug in 0 on the right, we get negative a, plus 0, plus 0. Right? We plug in a 0 for x, these two wipe out, done. A is 2. So we've got a is 2, which we got up there. Now let's plug in x equals 1. On the left-hand side, plugging in x equals 1, 4 minus 2 is 2. On the right side, you plug in a 1, gone, that's a 0. And over here, gone, that's a 0. So plugging in x equals 1, right there, we get 2b. So 2b, that tells us that b is 1. Now we're done with b. B is 1. Now, let's go for the last one. When x is negative 1, on the left side, negative 4 minus 2 is negative 6. On the right side, plugging in negative 1, gone. Negative 1 plus 1 is 0. Gone. Negative 1 plus 1 is 0. Only remaining term, negative 1 there. So in here, we get negative 2 times negative 1 is positive 2 times c, which tells us that c is neg 3. Neg 3. So in the case of linear factors, this is way faster when you have linears. And so we'll see that when we have irreducible quadratics, we have to use the traditional technique. There's not going to be convenient values for an irreducible quadratic. It's irreducible. It has no zeros. So it's not going to work for that. But we will see that if you have a combination of quadratic factors and linear factors, you can actually merge the two techniques, and you can do some convenient value and then create a less complicated traditional method for whatever doesn't get figured out with the convenient values. But it works very nicely, though, when you have linear factors. Okay, let's go to repeated linears. So repeated linears. So for example, something like x plus 2 squared. So up here, the gnarly looking box is saying that you need a partial fraction for every power of the repeated factor. So down here, x minus 6 is not repeated, so it's just going to have one PFD, one partial fraction for it. X plus 2 is repeated, and this is saying that we're going to have two partial fractions for this one repeated factor. So we have to have a fraction for every power of the repeated factor. So if this was x plus 2 to the 4th, we would have 4 different fractions. So let's try it. So with this one, we start with the inside again. So we're going to take our integrand and we are going to create a framework for this PFD. So x minus 6 is linear, not repeated, so it's just going to be a over x minus 6. Oh, x plus 2 is linear, so it's going to be b over x plus 2. But it's repeated, so we have to have another partial fraction for the second power. So we have to have a partial fraction for each power of that repeated factor. Now we do the algebra.
Wait, why did you put the square in the bottom of it?
So that's going to be how we deal with the repeated factor. So for each power, this is the factor to the first power. This is the factor to the second. This is the factor to the third. So we're going to have a constant over each of those increasing powers based on the number of repeats. So if this went to the 4th power, we would have d over x plus 2 cubed plus e over x plus 2 to the 4th. If. And then we do our regular multiplication to get our PFD equation. So our PFD equation, we multiply both sides by the left denominator. Multiply that to the other side. And when it multiplies to the other side, a bunch of stuff cancels out. When we multiply it to the first fraction, the x minus 6's cancel. So that's going to be a multiplied by x plus 2 quantity squared. When it multiplies to the second fraction, one of the x plus 2's cancels. So we'll have b multiplied by x minus 6 times x plus 2. And when that yellow block multiplies to the third fraction, the only thing remaining is the c and the x minus 6. So there is our PFD equation. So our PFD equation is where we decide traditional method or convenient value method. We're still just dealing with linears, so convenient value will work here. So let's go ahead and go for it. Now there's only 2 convenient values even though we have 3 unknowns. So let's see what happens. Now you know, if you're trying to find 3 unknowns, how many equations do you need? 3. If you have 2 unknowns, you need 2 equations. If you have 3 unknowns, you need 3 equations. So here's what we're going to do. We're going to use our convenient values. X equals, somebody tell me what the convenient values are? -2 and 6. Perfect. So what we are going to do then is just pick a convenient-ish value. Like 0, for example. It does not matter what number you pick. It will all work out. It will all come out in the wash. So those are the 3 convenient values that we're going to choose. And when we plug in -2 on the left, we get 64 equals -2 on the right, gone, gone, Negative 2 plus 2 is 0. 0 times anything is 0, so those two are gone. The only term left is there, which is negative 8c. That tells us that c is negative 8. Now we plug in 6. 6 on the left, we have 16 times 36. We'll figure that out in a moment. On the right, we plug in 6. This one is gone. This one is gone. Both of these have a 6 minus 6 in them. Over here, we have 8 squared. That's 64 times a. We can do a cancellation here. 16 goes into 16 once. 16 goes into there 4 times. So we can finish this off. A is going to be 9. Divide both sides by 4. Now let's plug in x equals 0. On the left, we have 0. On the right, when we plug in 0, we are going to have 4a. Plug in 0 here, we'll have negative 12b. Plug in 0 over here, we'll have negative 6c. Then, all we have to do is plug in what we already know. We already know those two, so those are going to get plugged in for A and C. And that will allow us to solve for B. So, I'm going to divide by 2 and move the B's to the left. I'm dividing by 2 and adding to the left. So on the right, I've divided by 2, so there's 2a. We came up here, a is 9. Minus, I divided by 2, so this is now a negative 3. Times c, and c is negative 8. So now we just have to solve that for b. So b will be equal to 18 plus 24, 42. 42 divided by 6 is 7. So there is our last coefficient. So even if we don't have 3 values, we can create one. You pick whatever number you want.
So if you have all the values except for 1, why can't you plug in a convenient value to find the last one?
You can plug in a convenient if value to find the last one. So that's what we did. So we did these two, we got these two unknowns, we still had to find B, so we had to plug in some other number.
What?
Because how else can we get to the B?
You're just creating an equation so you can solve for B.
So we know that if we have 3 unknowns, we need 3 equations. So if we only have 2 equations, we're only going to be able to solve for 2 of the variables, 2 of the unknowns. So we need that third equation so that we have 3 ways that the A, B, and C are connected. So to solve for 3 unknowns, you have to have 3 different dependencies. And this third, and it doesn't matter what the dependencies are. These are just convenient because they create a bunch of zeros. You could actually pick 1, 2, and 3 if you wanted. It'd be a lot more work. Like these convenient values work really nicely because they cancel out a bunch of terms. And we see that with that last one, when we picked 0, none of the terms canceled out, right? So we had 3 terms that we had to deal with. So that's why these convenient values are nice, because in each case, all the terms except for 1 cancel. But you technically could not use convenient values and use any values. You're just creating a dependency between the three unknowns. So let's finish this one off. We can squeeze it in up there. So the integral then is the integral of, we found a to be 9, so it's going to be 9 over x minus 6. We found b to be positive 7, So that's going to be 7 over x plus 2. And then we found c to be negative 8. So that's going to be negative 8 over x plus 2 squared. Okay. Now, I'm going to write this. I don't have a ton of space, so I'm going to write this strategically right off the bat. So we said that this is going to be 8 times x plus 2. I'm going to write it this way. Instead of putting the x plus 2 squared in the denominator, because that's how we integrate, right? If we have a power of x that's bigger than 1 in the denominator, we just move it to the numerator and use the power rule. So now we're good to go. This is going to be 9 natural log of x minus 6 plus 7 natural log absolute x plus 2. And then for this one, we have to use power rule. So we add 1 to the exponent, getting a negative 1, and divide by that new exponent. So add 1, get negative 1, divide by negative 1, making that positive 8. So we're going to have 8x plus 2 to the negative 1. X plus 2 to the negative 1 just means 1 over x plus 2. So there is the antiderivative. All right, so any questions before we go on break? So very prescriptive method, very sort of algebraic, not quite so web-like some of the stuff we've been doing, very, if this, then that. So as you do a few of these, you'll find that it's, pretty easy compared to trigonometric substitution, or what we're going to do next class, improper integration. All right, so let's take a 10-minute break. Pause. 3 values if you're going to do the convenient value method, or if you do the because there's only one convenient value, you would have to pick 2 other randos. So maybe the traditional method would be better in this case.
Okay.
But you could absolutely just pick 2 other randoms. Yeah. That will work.
This isn't too easy numbers to pick.
Yeah, so, and sometimes if you look, it's all x minus 2s. So 3 is a good number to pick because 3 minus 2 is 1.
Oh.
Right? So it's not technically a convenient value, but it's pretty convenient because it creates a 1. So but you can't pick anything, so the ones you picked, they would work totally fine. Yep.
Question?
Yep, that's going to work. So let's see. So yeah, let's see. So that's going to be that. True. That's going to be true. That's true. So we plug in. What do you plug in first? Plug in. So if you plug in 2, then that can be. Oh, I see. That's the column. Gotcha. Okay, so that's 4 equals c. Totally. And then you plugged in -2, so your left side will be 4.
Oh, wait, no.
Right, so you're going to have a little equation there.
Yeah.
You'll have an equation that I'll start to catch up to you all.
Wait, can we get a couple more minutes?
Yeah, go for it. Yeah. I'm just going to write down the structure first.
I actually.
Yep, that one is squared, so we plug in 3. So on the left side you have 9, and then 3 minus 2 is just 1. So you have A plus B plus C. Plus that C. Yep, so you could put plus 4 there. Yep, you can do that. And then
Choose
pick-
another random
Yep,
number.
pick another random number, so you can pick 0, you can pick 1, whatever you want.
Don't pick 0.
Okay,
Not a good idea.
so the left side when you plug in 0.
Traditional.
Zero.
You did traditional.
So 4A.
Traditional.
Minus 2 here, right?
Oh, yeah. So minus 2b plus 4.
Yeah, exactly. Yep. You. Power rule. The power rule. It's possible that A is 0. I don't think it is though. Let's
As long as you're doing, I'm basically saying that C is 0.
You get 16A minus 4B.
I don't know anything else. I got 4 for C.
Yeah, that's what I'm saying.
No, it stays there. That's good. And then 16A minus 4B equals 0. It's your subtraction. Subtraction is a thing that's always causing us grief. That looks very good. I don't know, I think that's right. So I think the technique I'm going to use is going to be a hybrid. I'm going to do one convenient value and then switch to traditional.
Okay.
So you can do all sorts of weird different combinations. So
Definitely can't teach that.
all of you got to the point when you plugged in your convenient value of 2, you got your C value. So if we plug in that convenient value of 2, we are going to get that C is 4. So here's how I'm going to switch back to the traditional method. So I'm going to say, okay, C is 4. So I'm now going to go back up to this equation, plug in the 4, and then I'm going to subtract it off to the left so that anything that doesn't have an A or a B is going to be on the left. So I took the 4, plugged it in there, moved it over. And now over here, we have to multiply this out, so we'll have ax squared minus 4ax plus 4 times a plus bx minus 2b. So now we've got a traditional setup, but we only have 2 unknowns. And watch how sometimes this traditional method can work really kind of fast. What is the coefficient of a on the coefficient of x squared on the left? The coefficient of x squared is, what did you say?
She said it was 1.
1. 1. And what is the coefficient of x squared on the right? Just a, right?
Yeah.
Just a. So we already have, so the coefficient of x squared here, coefficient of x squared there. So now we already have a. We didn't have to do much. And now let's go for the coefficient of x. On the left is 0. Coefficient of x over here, I see negative 4a. There's an x plus b. And so this tells us if a is 1, what does b have to be then? 4. And so now we're done. Now we have all 3 values. And so you can do the convenient value-ish method where you pick 2 randoms. Works totally fine. Here, 1 convenient value, and then I went traditional. Like, there's all sorts of different ways you can get at it. All right, so let's go back and look at our integral then. So we are going to have the integral of A divided by x minus 2, so that's 1 over x minus 2. And then B, so that's 4 over, and I'm going to write this as 4 times x minus 2 to the negative 2. So we're going to have to use the power rule. C is 4, so then plus 4 times x minus 2 to the negative 3 dx. So our final answer, natural log, absolute, x minus 2. Then we do the power rule twice. Add 1 to the exponent, we get negative 1. Divide by that negative 1, that's going to give us a negative 4. And a power of negative 1 just pushes that factor into the denominator. So 4x minus 2 to the negative 1. Similarly, for the last term, we add 1 to the exponent, getting negative 2. Divide by negative 2, that's going to give us a negative 2. 4 divided by 2 is 2. This is to the negative 2, so I'm going to write it. Usually we like to write it without negative exponents. So we would put it back in the denominator. And that will be our antiderivative.
If we answered it with a negative exponent, would you mark it wrong?
Nope.
Okay.
Definitely not. But it's, yeah, traditionally we like to not have negative exponents, but
Wasn't one of the integration techniques to remove negative exponents?
yeah, it is. Does that make any sense?
Did you get it?
Making sense?
I'm just trying to see how you combine the processes from the step to the step.
So I plugged in, I found C to be 4, plugged in the 4, there's no A or B in it, so I moved it to the other side where there's no A's and B's. So I took the 4
okay,
and
yeah.
made that x squared minus 4.
Okay, I see that now. Thank you.
Yeah. All right, I think we're ready for irreducible quadratics. Let's go, irreducible quadratics. So when you're in your mind, when you're thinking of irreducible quadratics, we're thinking of quadratic polynomials that don't factor with real numbers. Or maybe even I should say don't factor, yeah, that's it. Don't factor over the real numbers. So the classics are the sum of squares. X squared plus 1, need imaginaries, x squared plus 5, x squared plus anything. Right? It's not factorable unless you happen to use complex numbers. So that's not what we want. So here is the big difference. When our denominator is an irreducible quadratic, the numerator is linear. So instead of just a constant, so up until this moment, our factors in the denominator were always linear, and we put a constant in the numerator. Even when we did the repeated factors, we put constants in the numerator based on the fact that that was a linear factor. So the idea is that we want to have the numerator be just one less. So if we have a linear factor in the denominator, we want the power to be one less, constant. If we have a quadratic in the denominator, we want the numerator to be one less, so it's going to be linear. So we're trying to create the most general, yet still proper fraction. So if we have a power of 2, to keep that a proper fraction, the numerator power of 1.
And does that work with like cubics?
Well, cubics can be factored. So all polynomials, regardless of the power, can be factored into linears and irreducible quadratics. So that's the fundamental theorem of algebra. It says any polynomial can be factored down to linears and irreducible quadratics. So we know, so if you have a cubic, it can be factored into something like this. So here we've got two factors in the denominator. One is linear, that x is linear. And let me just point this out because this is a very common thing to get confused. If this x right here has a power of 2, that's still a linear factor. That's x minus 0 quantity squared. So that's a repeated 0. That is not an irreducible quadratic factor. So if there's a 2, same idea, if there was a 3 there, that's a linear factor that's repeated 3 times. So we'd have a over x, b over x squared, c over x cubed. So it's linear. That's not a quadratic. No ax plus b on that. So here we're going to take out the integrand. Take out the integrand. And we're going to create 2 partial fractions. One of the partial fractions is going to be an a divided by x. And the other one is going to be a bx plus c. So that's an irreducible. How do you know that that's irreducible? Back from algebra.
It looks bad.
It what?
It looks bad.
You can't factor
It
that.
looks bad. You can't factor it. How do you know you can't factor that over the reals? There is something that discriminizes zeros.
The discriminant.
Oh, the discriminant. If the discriminant is, what does the sign have to be on the discriminant to create a polynomial that doesn't factor over the reals?
Negative.
Negative. Right? When you do that quadratic formula, you get the square root of b squared minus 4ac. If b squared minus 4ac, which is the discriminant, if that's negative, then you need imaginaries. So if you had to prove that this was irreducible, you would look at b squared minus 4ac and show that it's negative. So here b squared is 4 minus 4 times a is 1, c is 2. So this is negative 4. That's less than 0, therefore irreducible. So if you're not sure whether a quadratic is irreducible or not, you check the discriminant. If the discriminant is negative, then you know it's irreducible. All right, so now they told us it was irreducible here anyway, but so we are going to create a PFD that looks like this. The linear factor gets a constant numerator, and then the irreducible quadratic factor gets a linear numerator. So it's going to look like this. And so obviously for an irreducible quadratic, there's no convenient value.
But if it comes out positive, can it still be irreducible? Just not.
Nope, it can be factored. Yeah. It might not be factored in a nice way with integers.
That's what I was gonna say.
Yeah. It could be nasty, x minus,
3 over 2.
whatever, some freaky fraction or some
Minus a 12.
irrational number, x minus square root of 2 times x plus square root of 2, something. Okay, so that is going to be the layout of our integration of our partial fraction decomposition. So now we're going to do the same thing we did before. We have to create our partial fraction decomposition equation. So we still do exactly what we've done before. Multiply both sides by the left denominator. The left denominator is going to cancel an x with the first term. And we're going to go traditional method, so I'm just going to, I see pretty easily that I just have to multiply by, I dropped an x, but I'm going to multiply by that 2 right away. So this whole thing got multiplied by a. When we multiply that denominator by the second part, we're going to have bx plus c multiplied by just x. I guess I could multiply that by x pretty easily too. So x times that is bx squared plus cx. So there's our PFD equation. We always get the PFD equation the same way. We multiply both sides by the left denominator. Multiply by that left denominator, all the fractions get cleared out. And now if we're going traditional method, which let's do that here. Let's just go traditional. So power of x squared. We've got an x squared there, got an x squared there, and there. So if we look at the coefficients, coefficient of x squared on the left is 1. Coefficient of x squared on the right,
A plus B.
a plus b. So we look at all the x squared terms and then add their coefficients. So that's going to be a plus b. And then we're going to go to the linears. So I'm looking for everything that has just an x to the 1. All right, so on the left, the coefficient of x is 3. On the right, I see 2a plus c. And then our last one, constant there. Oh, only one constant on the right-hand side, so we have 2 is equal to 2a. And that's going to give us the value of a immediately. So let's go. A is 1. And if a is 1, what is c? Question?
Yeah, not about C though.
What's your question?
If A is 1, then that makes B 0. Can you have that?
Mm-hmm.
Okay.
Mm-hmm. Mm-hmm. Yes, you can have, and you'll notice that especially with the irreducible quadratics, because you've got, it's very common with the irreducible quadratics to have one of them be 0 up there. With linears, you're not going to have that. Unless you have a repeated root, then you might have it for some of them. But okay, so A is 1 and C is 1 also?
Yeah.
Okay, so let's see what that gives us in terms of our integral. Come back up here. We're going to have the integral of a divided by x, so that's 1 divided by x. Oh, good. 0x plus c, so that's 1 over x squared plus 2x plus 2 dx. All right, so now we have an irreducible quadratic in that denominator. The only way we have to deal with that irreducible quadratic is what we did at the beginning of class. First two problems, completing the square. So this is going to integrate to natural log absolute x. And then we're going to complete the square in here. And what is the constant that we need for these two x terms to make it a perfect square trinomial?
1.
Just a 1. And I think you can see that if we do pull a 1 over there, we're going to have x plus 1 squared. So we have x plus 1 squared plus 1 dx. We're treating this as x squared. Let's go blue. So this is x squared plus 2x plus 1 plus 1. And that part is a perfect square trinomial, x plus 1 squared. And that new integral is inverse tangent. And no RCR, we don't even need RCR because the coefficient of x is 1. So we're going to have natural log x, natural log absolute x. This is going to be arctangent of the quantity x plus 1. If this x had a coefficient, we would do RCR and divide by that coefficient. If that was a 3, we divide by 3. It's not, so we don't. And then our integration constant, so there we have it. On the road to becoming integration ranges. On the road. Any questions on any of those steps? The plus C.
Professor Charles.
Plus Charles. Plus Charles. All right, let's go ahead and take a look at this one, where we have two irreducible quadratics. This is about as bad as I would put on a test. Two irreducible quadratics.
So it'll be on the test.
So, and these are y's. Oh my gosh, y's.
But it's just a variable.
Just a variable. I'm glad it's not z. Z is a pain.
What if the variable was y, but the differential was dz?
Then we'd be in trouble.
I
In
mean-
Calc 3, you'll learn how to do partial integrals. Calc 3. Sounds like a blast. So this is going to be ay plus b over y squared plus 1. So y squared plus 1 is irreducible. Anytime we have an irreducible quadratic, the form of the partial fraction is the largest possible proper fraction, so the numerator is going to be linear. We're trying to generalize that fraction as much as possible, so it's going to look like that. And then we're going to have cy plus d. So there is our setup. We're going to multiply by the left side's denominator, creating all sorts of madness. Ay plus b times y squared plus 2 plus cy plus d times y squared plus 1. So that is the PFD equation. PFD equation, multiply both sides by the left denominator. Now with these, convenient values is going to get us nowhere. So we're foiling. We're going to do some mad foiling. So our PFD equation, we're going to make it look pretty messy. We're going to have ay cubed plus plus 2 plus by squared. I can do this. Plus by squared plus 2ay plus 2b plus cy cubed plus dy squared plus cy plus d. So there is our lovely PFD equation. PFD equation. How many equations are we going to need? 4 unknowns, A, B, C, D, so 4 equations. Question?
Yeah, this has to do with this question, the last question.
Mhm.
So on the, when you have 1 over y squared plus 1 times y squared plus 2,
Mm-hmm.
why do you have ay plus b in the numerator? Why is it not a over numerator plus by?
So
over
when the
numerator?
denominator is linear,
Uh-huh.
you put a constant up top.
Uh-huh.
But when the denominator is a quadratic, you put a linear up top. You always want the power between your factor and your numerator to be 1.
Okay.
You want the largest possible, the most general fraction that's still proper.
Okay.
And so if we have a quadratic, this is always linear. And if that's linear, that's always a constant.
Okay. And so if the denominator is highest power is to the power 3.
Which can't happen because we can always factor it into
Okay.
powers of 2 and powers of 1.
Got it. Okay.
So 3, 4, 5, you can factor it. Maybe you don't want to factor it. If you have a power that's 5, you're hoping it's already factored,
Got it.
right? But everything can be reduced to factors that are irreducible, quadratic, and linear.
Is this the hardest you'll give us on the test?
Yeah.
Like,
Yeah, 2 irreducibles. It'll take long enough. So when we look here, what is the coefficient of the cubic term on the left?
0.
0. So we'll have 0 equals a plus c. And then we're going to go to the quadratic factor. I only see 2 there. So once again, 0 on the left. And then we'll go to the linear
D.
factor.
That's D.
Not C.
D, thank you. So then we're going to go to the linear factor. And the linear factor is still 0 on the left. And linear on the right, let's see that. Well, that and that, I guess that works. So what is that? 2a plus c. 2a plus c. And then we go to the constant term. On the left, that's 1. And on the right, constant, 2b plus d. 2b plus d. So we notice a couple of pairs here. These have the same letters, and these have the same letters. So we're going to group them together. We'll take the difference of each to eliminate a variable. So the purple ones, let's do that first. So I'm going to do third equation minus second equation. So equation 3 minus equation 1. Everyone follow? So 0 minus 0 is 0, 2a minus a is a, c minus c is 0. So 3 minus 1 gives us a is 0. And if a is 0, what is c? If a is 0,
C is 0.
c has to be 0. Now let's go to the greens. Let's do 4 minus 2. So equation 4 minus equation 2. We're going to do 1 minus 0. We're going to do 2b minus b. And we're going to do d minus d. So b is 1. If b is 1, d is b is 1, d
-1.
is -1. So now we have all 4 of our coefficients. So we will have, this will all equal the integral of, let's use different colors. So this will be the integral of ay plus b. So 0y plus 1. So 1 over y squared plus 1 dy. Break it into 2 integrals, why not? cy plus d. cy plus d, ooh, that's negative. So if that's negative, we're going to put a negative out in front. 1 over y squared plus 2 dy. Okay. What is that first integral?
Inverse tangent of y.
Just inverse tangent of y, not too bad. The second one, our strategy has been to force the 1 into the constant position. So I'm going to factor out a 2. And when I factor out a 2, it's in the denominator. And it puts a 2, right? The idea is that we are going to multiply by 2 over 2, and that 2 that we factor out leaves the 2 in the denominator. But we always then write it as a single square. How can we write y squared over 2 as a single square? Over root 2. Y over root 2 squared. So y over root 2 quantity squared plus 1. That is just an arctangent with RCR. So we're going to go up here. We're going to end up with arctan of y minus 1/2 space for RCR arctangent of y divided by square root of 2 plus c. And the derivative inside the parentheses here is
1 over square root of 2.
1 over square root of 2. We're dividing by 1 over square root of 2, so we multiply by the reciprocal. So that's going to put a root 2 right there. And so you could write that as root 2 over 2. And that is final answer. Question?
Could you have done that second part of the split integral using the 1 over a squared plus x squared method?
Here?
Yeah.
Definitely. Yep. You could have, yes. Make that better too.
With ABCD, I tried solving not with elimination but with substitution, and I didn't get the same thing.
So you must have done some sort of substitution. You probably lost the sign. So if you saw, you could use substitution. Solve this for A. A is negative C. Plug in negative C right there. So you're going to have negative 2C plus C, which is negative C equals 0. So you're going to get C equals 0, which means A is 0. This one, if you say B is equal to negative D, you would plug in negative D there, so you're going to have negative 2D plus 1D, which is negative D equals 1, so D is going to be negative 1. And if D is negative 1, then B is 1. So it will work if you don't goof any signs, which is always the challenge. Do an area. So they give us a curve. I've graphed it for us so we can see what it looks like. That messy curve. We just want to find the area beneath that curve, which is the first application you ever learned in calculus. You can use the integral to find the area beneath a curve. So the area here is the integral from 0 to 1 of this function. So they've already factored it for us, and it's factored into a linear, x plus 1 is linear, and an irreducible quadratic. So it's already been factored down for us. A linear and an irreducible quadratic. So let's write down the next step, and then I'll let you guys try to solve it. So this is our first step, is that we take our integrand, and we're going to write it as a over x plus 1. That's the linear one. And then for a quadratic, it's always going to be a linear up in the numerator. All right, so see if you can solve that one then. Let me know if you're struggling on anything. Solving that system. that should be, oh yeah, just x plus 1. That's good. That's good. Yep. Yep. You're right. Totally on track. Let's see, picking some values. Picking values. Now multiply all that out. Set up your. Oh, they look nice. I don't remember the answer. Just make sure these are in parentheses.
Much easier than Tricks Hub.
And this should be a BX, right? Or something. I agree with that. The B, right? Because that's this is all being FOILed, right? So BX times that, and then BX times 1. So something's there. And this CX, yeah. Wait, what? Wait, what is it doing?
What?
Updating.
Really? In the middle of class? You gotta be kidding me.
Since it takes 5 minutes.
What? My gosh, I have to write on a whiteboard?
I'll see you on Tuesday.
What the heck? So what did it do to my recording?
Killed it.
Oh, it's gone?
What does it look like on the computer?
Yeah, is there any way to like cancel that and say, no thank you? Leave my firmware alone? My computer just looks like my computer, normal where I was. That is absolutely bizarre.
Is the recording still going?
Do not turn the power off.
No.
That's a good question. I didn't look to see if the recording was still going.
How will we turn
Yeah.
the power off?
The recording is still going. Don't turn the power off. Tough.
That is not.
That was just a suggestion.
This is where we have problems.
Besides, they're more of a suggestion.
Now the screen is gonna be just green.
Yeah.
We'll see. You're gonna come back. Now it's not even gonna turn on. It's so
It's
mad.
okay, you'll just ask Aichi to buy 40 more new line
We'll
boards.
see. We'll see what happens. You guys keep trucking. I'll figure this out. We'll use masterful problem-solving techniques.
Oh.
Loading. Wait a minute.
I'm just.
Oh!
Take that.
Watch it not let you write.
Yeah, watch it. They really weird. Ah! I did it again! Somebody tell me what that equation, what was the left side of that equation?
X minus x squared.
And the right side, once it's all multiplied out, is?
AX squared plus A plus BX squared plus BX plus CX plus C.
Thank you. All right, so we're going to set up our equations here. Coefficient of x squared on the left is -1. Coefficient of x squared on the right is a plus b. Coefficient of x on the left is 1. Coefficient of x on the right is b plus c. Constant on the left is 0. Constant on the right is a plus c. So if we add, no, let's subtract. Let's get rid of A. So if we get rid of A, I'm going to take equation 3, and I'm going to subtract off equation 1. So 0 minus minus 1 is 1, A minus A is 0, and then C minus B.
Because the substitution was wrong.
So now we have this with a C and a B, and if we combine it with this one, C plus B, I'm just going to rewrite it so that it's stacked properly. We're going to get 2 equals 2C, so C is 1. And if C is 1, A is negative 1. And if C is 1, B is 1. Did you all come up with those? 1, 1, negative 1? 1, 1, negative 1? I can't believe it. These boards are such a...
A nicely worded email to IT.
Yeah. So,
I'm following along.
say again?
Wouldn't B be 0?
Oh, I subtracted wrong. So if A is negative 1 and we add it, yes, B is 0. Thank you, Ari. B is 0. B is 0. All right, so what is, somebody tell me what the integrals that we're left with are, then 1 over,
1 over
X plus
negative 1 over x plus 1.
and
Plus 1 over x squared plus 1.
From 0 to 1.
Yeah.
0 to 1. All right, so pretty straightforward here. We get minus natural log absolute x plus 1. Here we get arctangent of x, 0 to 1. Notice that if you plug in 0, you get nothing. 0, you get nothing. Natural log of 1 is 0, arctan is 0, 0. So all we care about is the 1. So we get minus natural log of 2 plus arctan of 1, pi over 4. So there is the area.
And you can't simplify that anymore, correct?
Yeah, that's it. That's as far as we can go.
That means that you're exactly right.
That's as far as we can go. That make sense?
We can have absolute value of this one.
Absolute value of 2.
Yeah.
You could, yeah, you don't need it because 2 is positive, but
Yeah.
you could.
But we could.
And you could, if you wanted to, deal with negative exponents, you could make this natural log of 1/2 plus pi over 4.
Oh.
You could pull that up as a exponent.
Okay.
Pearson would want you to do natural log 1/2.
There are definitely some places where they love log rules.
Pearson's using.
Have you? Is anyone? I'm surprised I haven't heard from anyone yet in the trig substitution section. There's a couple of.
Because nobody's done
No, because this is coming up as an exponent, so 2 to the negative 1. 2 to the negative 1 is 1/2.
No, the viewed example on the trig substitution homework is like awful.
Yeah, there's a couple of trig substitution ones where I'm surprised no one's asked yet. Maybe I'll hear from you all over the weekend.
Because my method is easier.
Come on, firmware. All right, so the last problem that we're going to do is this volume problem. And OTA completed.
What?
If you need a person page.
Yeah, that would be helpful. Thank you.
Yeah, of course.
All right, so we're gonna integrate something that looks like, it kind of looks like a catenary, but it's not.
Looks like a what?
Catenary,
Okay.
It's a
catenary
catenary.
hyperbolic cosine, the hanging table, the sleeping cat. Appear.
It's gonna after you've written everything down.
There is like 6 minutes left of class.
We can do it. I believe. I believe. All right, so the problem says we've got this region and we want to revolve it around the x-axis. So we're going to take that region, rotate it around the x-axis. We're going to create like a, kind of looks like a spool.
Like an hourglass.
Like an hourglass, solid hourglass. And the function is 1 divided by the square root of 4 minus x squared. Oh my goodness.
Oh, my word.
Killing me, new line. Okay, so we're going to go around the x-axis. What is the technique that we're going to use? Disk, washer, or shell?
Disk.
Disk. So the disk method, are we going to use a vertical or a horizontal element? Vertical element, because it's touching, so when it rotates around, it's going to create that disk. The radius of that disk it creates is right there. The function is the radius. The function is the radius. We know that the area of a disk is pi times the radius squared. So in this case, pi times r squared. We're going to have pi times, oh, that squared is pretty nice. You get that? Now, the volume is going to be the integral of the area. So the volume, and we're going to use some symmetry here. Now, when this rotates around the x-axis, there's just as much volume to the right as to the left. So I'm going to do 2 times the integral from 0 to 1 of that area. The pi can come out in front. And I'm actually going to factor out a -1 also, so that I can write the denominator as x squared minus 4. Who the heck wants to factor when we have a constant first? We want to put it in descending order. It's way easier. So we have that. So -2 pi. And then we're going to factor this denominator into...
It's like trigonomic substitution, you can use it.
You could use trig sub here. So that would be, if we're doing PFD, that would be our setup for the integral. And then we're going to say, okay, let's take the integrand, and we're going to do PFD with 2 linears. These are going to feel real easy now. So that's going to be a over x minus 2 plus b over x plus 2. We generate our PFD equation by multiplying by the left denominator. The convenient values, x equals -2, plug it in right there, and we get 1 equals -4b. So b is -1/4. The other convenient value is x equals 2. That's going to give us still just a 1 on the left, a 4a. So we're going to get a is +1/4. So that tells us that our integral, so the volume, we're calling it b, -2 pi, integral 0 to 1. Nothing's changed yet. All we're doing is rewriting the inside here. Let's factor out the 1/4. We don't want that 1/4. That 1/4 is going to factor out with a 4 in the denominator. And we're going to have, let's see, right here. So a, that's going to be 1 over x minus 2. But then b is negative, so it's going to be -1 over x plus 2. I factored out the 1/4. So we have -pi12 times the quantity ln x minus 2 in absolute value minus ln x plus 2 absolute value from 0 to 1. -pi divided by 2. Plugging in the 1 gives minus natural log of 3. Plugging in the 1 here gives 0. 1 minus 2 is -1. Absolute value of -1 is +1. Natural log of 1 is 0. Plugging in the 0, so now we're subtracting off what we get when we plug in 0. So plugging in 0 here, absolute value of negative 2 is 2. We're subtracting this, so that's going to become a plus. And we're plugging in 0. Okay, that's going to be a natural log of 2 also, so those are going to cancel. Those both go away. So we end up with positive pi ln 3 divided by 2. Carter?
Wouldn't it not be divided by 2 since you use symmetry? Because then it would turn because the integral goes from -1 to 1, right? I think you use symmetry.
Yeah, so I went negative 1 to 1, I went 0 to 1 and multiplied by 2.
Okay.
So
Two each.
let's see. So this part, so this 2 right here is the symmetry.
Oh, okay.
That 2 is the symmetry, and the pi and the -1 are coming from that.
Alright.
So that 2 is a symmetry 2. It's sim.
Can you scroll back down?
Yes. So that's symmetry 2. So there's our volume. Whew. And we've updated our firmware. I feel so much more alert.
Hey, maybe it'll stop flickering.
Hmm?
Maybe it'll stop flickering.
That's a good point. That is a good, maybe it will. That's a,
Watch it flicker right behind you.
yeah. We'll see.
If not,
I'm not optimistic.
they just update in the middle of class for no reason.
Right. I don't, I thought the IT said that they were gonna do all updates in the middle of the night.
Maybe they just like decided to update them right now.
Yeah.
So we'll just start making copies of